All right, so last time we went through how to construct convex hulls in higher dimensions. And so at this point, we now have a pretty good concept of what is a convex hull, how do we work with convex polytopes, how we can construct these things. And we've seen a couple of different queries that we can answer or ask about convex polytopes, specifically linear programming. Now, previously, when we looked at linear programming, we looked at the problem where we went into it sort of, just completely cold, weren't allowed to do any pre-processing or calculations in advance. And then we wanted to answer that linear program query, just given the input points or half spaces for our polytope. But today, we're going to look at the problem of how we can take a convex hull of some polytope and use that to speed up linear programming queries. And the amount that we will be able to speed them up will turn out to be exponential. So we'll go from, say, linear time, have to scan through all the points, to, say, log of the number of points on the convex hull, which is a pretty good deal. So in some sense, we already have some idea. So the lecture today is linear programming with convex hulls, and some of the fun things that we can do with it. Or another way to say this could be, so you've got a convex hull, now what, right? Right. So in 2D, we've already kind of talked about this, but I want to go through it in some more detail to talk about how we can use a 2D convex hull to speed up a variety of linear programming queries. And one of the simplest linear programming type queries that we would usually care about is testing whether or not a point is contained inside a convex polytope or not. So usually we're given some vertex polytope or maybe a half-space polytope. You want to say, okay, test if this point is contained inside there. So here's kind of a picture. I'll just draw some crazy, it's probably not very convex looking. There. So this is some polytope. I have some query point here. We'll call it Q. And then we want to check, this is our polytope P. We have the point membership. Classification problem, sometimes called PMC, is we just want to say, is Q in P? All right, well, so that's the basic problem, and we've already seen how you can think of it in terms of linear programming. But today, we're going to look at how we can answer this problem for the case of convex hulls, or for if we have a convex hull already calculated. Now, the algorithms I'm going to talk about today will only be stated for 2D and 3D, and the reason we won't go into higher dimensions is that higher dimensional convex hulls are kind of useless because they're just enormous. So in order for this to actually be a net win in higher dimensions, so that it would actually be faster than, say, like Seidel's algorithm, you'd have to be querying with an enormous number of points. So you'd have to be querying with like on the order of n points. And if we're actually going to do a query with that many points, there are ways that we could amortize it over the course of the entire convex hull that might be a little bit faster. For example, we could actually compute the convex hull of the 2 point sets in parallel and then use that to, amortized compute all of those linear programming queries. So we're not going to worry about those high dimensional cases. We're going to look at sort of the low dimensional 2-3D case where we're going to be just testing a few like sporadic points. So we don't know them beforehand, but we're going to do this pre-calculation so that someone gives you a dynamic query, you can answer it very quickly, right? So, okay. So here is an algorithm for 2D polytopes, right? I will not say how this works in 3D yet, but we'll come to it in a moment. So in 2D, here's the idea, is I'm going to pick some vertex here. We'll call it P0, right? Doesn't have to be any particular vertex of this polytope. And then what we will do is use a binary search to figure out where this point Q is contained, or sort of which face is visible from Q. So we're going to draw these little fans going off here. And then if we look at these fans, right, each of them is just an oriented line. So if we go from, say, P0 to point Pi, what we can do is check whether the point P or the point Q is to the left or to the right of Pi. If Q was to the right, then we can just recursively binary search on this half of the polygon. Otherwise, we'd recurse on this half. And then we just keep cutting it in half until eventually we now know that there's going to be one single phase, Pi plus 1. And then we can just do one final left-right test against Q, and that will tell us if Q is contained in the polygon or not. So here is our 2D polygon PMC test. So we'll call it PMC 2D. So this is the subroutine that we're going to use. So the input is going to be a polygon represented as an ordered list of points and a query point Q. And initially, we'll create two variables here, low, which is going to be like the lower bound on this binary search, and then high, which is the upper bound. We'll initialize it to n. And then we just do the ordinary binary search routine. So we say while low is less than high, compute the midpoint, which is just the floor of the average. Right? So you just take the average, round it down. Then we'll say if orient P0, P mid, Q is less than 0. So this would be in the case where Q happened to be to the left of the line. Then we have to move the upper bound to mid, right? So we'll basically set high to mid. Otherwise, assuming no degeneracies here, right, for now, then we'll just set the low to mid plus 1. And then at the end, we'll just return. So we just loop here until we finally narrowed the bound so that there's exactly one interval that happens to contain this little fan with Q. And then we can finally just return the orientation of P mid plus 1, assume circular indexing here, and Q less than 0. Because we're basically going to just check whether or not this thing is to the left of this line segment or to the right of it. So if Q was to the left, then we'll say that it's outside. If Q is inside, then we'll say, or if Q is to the right, we'll say it's inside. So I should actually probably make this greater than 0. In fact, another way I could write this, I could just say return the sign of this thing, right? So that'll give us in, out, or on for the point Q, allowing us to classify it relative to the polygon. How long does this take? Well, every time we do one of these iterations, we cut down the size of this interval by half, right? And when the interval gets down to 1 element, we're done, right? And so the total number of iterations here is log of the number of points on the convex hull. So the time complexity here is order log n. So, OK, great. We can compute point membership tests. But this is actually not too far removed from general purpose linear programming. And here's why. So if instead of taking a point here, Q, that happened to be at some finite value, if we took a point at infinity and then ran the same algorithm on it, well, what's going to happen? So suppose instead of Q, we now have some abstract direction here. We'll call it D. All right? So D is going to be some point at infinity. So here's the question. So we'll say, what is PMC of this polygon and a point D? Right? Well, D at infinity. Well, if we run this algorithm, it's always going to return that it's outside of this thing, right? Because when we do this final orientation test, if we have a finite line here and we have a point at infinity, right, at some point it's going to select whichever facet happens to be pointing away from them, right? So here's kind of a picture that might help visualize what's going on. If we take each of these vertices, we imagine extending these lines out by some amount. Then we have some angle here, right? We're actually should actually draw these lines perpendicular. So if I take two lines which are perpendicular for each of these surfaces, then I have these little fans that stick out along each vertex. Right? And so the last value of mid, right, as I'm running this binary search, right, the value at which it gets stuck in for this point D is going to correspond to the normal fan here in which this vector D is going to be located. So if I take this vector D and I basically classify it to the left or to the right of each of these lines, eventually it's going to get stuck in one of these little cones here, right, or these like little, fans sticking out of the polytope. And so it will end up here. So what is that vertex, right? This vertex, this normal fan, one way you can think about it is that this is the space of all possible linear programs for which it happens to be the solution, right? So if we think of this vector D, this point at infinity, as being the objective function of our linear program, then what we're doing with this binary search is we're going to keep looking over each vertex until we eventually find this one vertex, which happens to be the solution to that particular objective function. So here's what we can do if we want to do linear programming using this exact same algorithm, is that we're going to modify it a little bit. So here's linear programming. We'll say linear programming. It'll just be find the vertex V in P such that we'll write this. I used D there. We'll say D transpose V is going to be greater than D transpose U for all other U in P, right? Or another way of saying this is that really this D here is a sort of supporting vector, right? So that's what these little cones are. So we're going to call this new thing linprog2D, right? This is all going to be the same. Again, here's what we're going to do is instead of Q, we'll feed in a D here. We can use the exact same orientation test as before. And then when we're all done, we'll just return P mid. So that will actually solve this whole thing. And that's it. So in a very simple modification to the original point membership test, we can now answer linear programming queries. Again, in order log n time, right? Because we're basically doing the exact same algorithm, except instead of doing a binary search on this line against a finite point, we're doing a search on a point at infinity. So, okay. So that's pretty cool. What can we do with this, right? So if we have one of these points, we can also find a related issue. If we have one of these like tangent faces, right, or one of these faces which can see the point, right, we can actually locate the closest face on a given polytope to any query point. So another way to think about what's going on here is that when we do this search with these fans, we're actually finding the face which happens to be closest of all of the faces to the query point. And with this linear programming ability, we can actually think of this as finding an extremal point in the polytope along some axis. So here's how we can combine those two ideas together to calculate tangent lines as you had to do in that homework. It is one way to do it. There are other options here too. All right? So this is the idea. So using the linear programming technique that we had before, and then the point membership technique, we're going to put them together. And so here's the high-level idea. I will draw a picture. There's a lot of stuff going on here. So ignore the point at infinity. So the first step, so tangent calculation. This is one way to do it. There are many, many ways to compute tangent lines for a point, right? I think we even talked about some other different ways last time too, right? So, but this is the one I'm going to talk about today because it ties into linear programming. So the first step is we find the closest face. To Q. So in this case, we're going to be locating this face right here. We'll call this axis F, right? So it'll have two directions. We'll say this one, just call this F plus, and this direction F minus. Step 2, project the polytope onto plus minus f. Or that's it. Done, right? So here's how this works, right? I mean, what we're going to do is we first use a modified point membership test, or basically a linear programming search, to find the closest face. Once we have this face, we now have the axis here, which is the directions. If we squish this polytope onto this axis, the extremal vertices here and here, or wherever it is, I guess it's maybe not quite those two, but somewhere along this thing, there will be 2 points which are farthest away, this one and this one, say. These 2 extreme points along this axis f are the tangents to Q. All right? So that's it. So we just do a bunch of binary searches over and over again. What's the cost of doing this? Well, finding this point here is a log time operation. Finding the 2 tangent lines, again, is a log time operation. So we can just keep using this same binary search trick over and over and over again to speed stuff up. OK, so we now know how to do tangent calculations between a convex polygon and a point in 2D. Right? In 3D, this is harder. Yeah?
Just a quick question. How exactly are you binary searching for the projection of the segments on?
We just use this algorithm right here, right? The linear programming. Because finding the extreme point, the projection here, this is just linear programming in this direction, right? We're just going to project it onto the f plus axis. That's all that's going on. So we have this. Think of this thing here as basically being like a vector pointing that way and a vector pointing that way, right? So what we do is we take this vector that goes in this direction. We use linear programming to find the farthest point in the polygon along that direction. That's the first tangent. Then we go in the other direction as far as we possibly can. That gives us the other tangent point. Once we have those 2 tangent points, done. All right. So that's how we do tangent calculations for a 2D polygon. Right? There are many ways that you can do this. This is just one way to do it. Okay? But the neat thing is that it's directly connected now to linear programming, right? So, OK. Right, so what's another thing that we can do with linear programming? Well, or another important question that you might have to ask about 2D convex polygons. One common issue is checking whether 2 of them happen to intersect or not. So oftentimes you might have, like, say, some video game or some simulation. You got a bunch of these like little polygons bouncing around. You want to check if they happen to be overlapping, right? And you would like to do this fast, usually log n time, right? So we can use this tangent calculation right here that we just did to speed up the intersection test between 2 pairs of convex polygons. So let's go through how this works. So we're now going to go. I'm going to probably erase some stuff here. I'm just going to erase this whole thing. OK. We'll draw a new picture. OK. Here's the idea. We'll start with 2 convex potatoes, right? We have maybe one here called P. We'll have another convex polygon Q. All right? Imagine that they're polygons. All right? They're just really finely subdivided or something. All right, so here is the concept. So first, this is going to be intersection test. You can think of this as like collision detection for convex polygons. Select any 2 verts P0 in P, Q0 in Q, right? And 2, we're going to compute tangent points. We'll call it P plus, P minus in P relative to Q, and Q plus, Q minus in Q relative to P. All right? So here's the picture of what's going on. Let me get 2 different colors here. So suppose this was some arbitrary vertex here. We'll call this one Q0. Similarly, we'll pick some weird vertex, call this one P0. So in P0, what we'll do is we're going to draw two tangent lines here to Q. We'll call this one, say, Q plus, Q minus. And in Q, we're going to draw these tangent lines to P here. We'll call this one, say, Q minus, or no, P minus, P plus. Right. So, okay, we now have these two oriented sections of this convex hull. And so then what we're going to do is we're just going to cut it, right? So we're going to forget about this point P0 and this point Q0. We don't even have to worry about them anymore. And then we're going to just slice away the rest of this hull. So we'll get rid of all of this stuff, right? We'll get rid of all of this stuff. And then we're just going to be left with these two intervals here. So we're going to be left with this chunk of points on this hull, and then this chunk of points on this hull. So basically, 3 cut out intervals Q minus Q plus, P minus P plus. All right, so this is the setup for the intersection test. So now what we have is we have these two intervals, that basically represent two chunks of the polygon. So I'm going to even erase the tangent lines. And the important thing is that these two intervals are all visible relative to one another. So we don't have to worry about like these extra points on the side of the hull, right? Any point that we pick here is going to be, in some sense, like visible from all the other points over there, right? And so what we'll do is for each of these intervals, we're going to subdivide them in half. So we'll pick some point here. We'll call it PM for midpoint. And then we're going to imagine that we just draw a triangle, right, like that. And we'll do the same thing here. So we're going to have this point QM. And again, we'll draw a triangle. And so these 2 points are halfway between the two intervals. Now, we have what's basically a triangle here and a triangle here, right? And each of these triangles is built out of 2 separate line segments. So what we'll do is we'll take each of these 2 line segments and compare them against each of the other 2 line segments and try to find the closest point. All right, so we're going to just look at these 2 finite sets and just find the closest pair of features, which we know how to do by brute force, basically, right? We can just go through, and for a line segment and a point, or a point and a line segment, or a point and a point, just for every pair of features on the boundary, test them against one another. And in this situation, there's going to be 3 cases. So 3 situations. So the generic one, and the one that will happen, most of the time, is that it's going to be a line segment is going to be closest to a point. All right. So for example, suppose that maybe the closest point was maybe there was some point on this line segment which happened to be closest to some point on this line segment, right? I mean, that's maybe not how I drew the picture here, but or maybe like this line segment happened to be the closest to this point QM, right? That could be one possibility if it happened to work out that way, all right? If that's the case, then I take the line segment and then I just recursively subdivide it. So I rerun this whole process again, just starting now with P plus equal to PM. So I just move that half of the interval so that now I'm going to zoom in on this feature here. And then we're going to repeat this whole song and dance again by subdividing this thing. So we'll basically subdivide this line segment again and then redo the whole story, right? So that's easy. The other possibility is maybe I have 2 parallel line segments, which are as close as possible, right? So the closest feature happens to be a line segment, right? So this is sort of 2 segments are close. In this case, then what I have to do is I just subdivide both of those 2 line segments. So I start from the pair of 2 line segments which would be close, and then I do the song and dance on those 2 things, and I recursively continue from there. And then the final case is the 2 closest features happen to be vertices, right? So our closest. In this case, I'm actually done, right? Because it turns out that if I have some vertex here, which is like as close as possible, this is actually a vertex on the convex hull. So any other vertex over there is actually going to be farther away than this one, and same for the other vertex. So the story's over, right? So I've actually found the closest pair of points then. And because every time I do one step over here, one of these intervals is decreasing in size by a half, the total number of iterations here, or the total number of times I have to do one of these subdivisions, is logarithmic, right? Because it's always going to go down by half. So the complexity of this intersection test that I've just sketched out here, did not write it in explicit code, but the complexity here of detecting if two convex polygons in 2D intersect is order log n, supposing that P has n vertices, plus log m, where Q has m vertices. So n is equal to the cardinality of P, m equals the cardinality of Q. OK, so that's pretty cool. This shows us that we can do a bunch of stuff with 2D convex polygons. Yeah?
So, sorry, you said the usual case is line segment closest to point.
Yeah.
Isn't it always, what's the intuition behind that? Because I see like a line segment and then you got points, but like wouldn't the points always be closest to the vertex on one of the ends?
Well,
how does that work exactly?
let me try to think about what's going on here. So we can think about this as that like we have, I mean, it's just because I drew a kind of funny figure here, right? But imagine it looked more like this, right? So suppose QM, like maybe it was like really finely subdivided like this. Then what you can think about is that imagine that there's sort of like these waves which are coming off from here, right? And so at some point, these waves are going to just hit this thing. There's always going to be a unique point. And in general, it's going to land somewhere in the middle of a line segment, right? So it'll be very rare that it ends up actually hitting a vertex that's the closest, right? So that's the reason that you should sort of think about this, is that essentially this is a quadratic function, right? Because actually what we're doing here is we're actually just doing quadratic programming, right? You can actually take exactly this problem of finding the closest pair of points, rewrite it as a quadratic program, and then just solve it. In fact, all that we're doing here is we're just sort of unpacking the quadratic program into a kind of algorithm here that has a sort of, funny geometric interpretation. But the algebraic thing that's going on is it's just quadratic programming. There's really nothing else, right? And this is a general situation, right, is that in 2D, most of these sort of linear programming or more generally quadratic programming algorithms that we would care about will really just turn into some variation of a binary search, right? Or another way that we can think about those binary searches is that we could imagine that we're starting with some sort of coarse approximation of the convex hull and then refining it down locally using the structure here, right, to sort of zoom in on it, right? So this is kind of the intuition for how we are going to try to generalize these techniques to 3 dimensions. Because the problem is in 3D, we can't really do a binary search like this because we're going to be dealing with planar graphs and doubly connected edge lists, and topology is weird and complicated. And so the simple type of picture here doesn't just directly port to the 3rd dimension, right? And it's also completely hopeless in higher dimensions, but we're not worrying about those for now. Okay? So what we've seen, right, is that in 2D we can do point membership tests, tangent line calculations, intersection tests, and etc., all in log n. So what can we do in 3D? It turns out we can realize pretty much the same time complexity, but the means by which we do it are a lot more complicated. And that is the subject that we will be digging into today. So OK, any other questions about the 2D stuff before I jump into 3D? No? All right, all good? OK. So here is the high-level idea, is that we're going to use this concept of refining a polytope, starting with some sort of like really coarse and crappy model, right? Like maybe just like a single tetrahedra for the entire convex hull. And then we'll imagine that we sort of subdivide this finer and finer and finer until we reach the ultimate convex hull, like some really fine-grained model. So we'll go from a very coarse model to a fine model. And then the way that we'll do these searches is that we'll want to evaluate our linear program on maybe this really coarse, crappy like convex hull, then we'll use that data to speed up a search on the next level of the convex hull. And if each level requires only a constant amount of additional work from the previous level, and if our first level was like really trivial, like constant size, then in the number of these levels, we will be able to answer our linear programming query. All right, so this is the high-level idea. So don't know if this is the right time to do it, but I have a video of this technique, which I wanted to show. I think I'll just go pull that up because it may help do this, because this is actually a very difficult thing to draw. So I got this really retro thing from the 1980s. I mean, like, these ideas were, of course, all discovered long ago, so it's... can you see this? Let me go turn off the lights. All right. OK. Let me see if I can adjust this. All right. Yeah, it looks good. Yeah. All right. Is it playing? OK. Whatever. All right. It's like a little bit glitched, but looks fine.
Here we illustrate Kirkpatrick's planar point location data structure on a triangulation with 32 vertices. The second level of the structure is copied from the first. These vertices and their incident edges are removed. This creates polygons that must be triangulated. After triangulating each polygon, we link the resultant triangles with all of the triangles directly below. We also place links now between triangles that are present in both levels. At each level, the vertices to be removed are colored red. The edges incident to the red vertices, which are also removed, are colored yellow. Red edges fall in from the sky to retriangulate the resultant polygonal regions, and green links link overlapping triangles. Now you can see the completed hierarchy. By removing the triangles, you can clearly see the search structure that has been built.
Well, you probably could see it clearly if the video wasn't so low quality.
The beam of balls represents the target of the point location query. The query is carried out by moving a large ball from the top of the structure to the bottom, always passing through the same triangle as the beam
Okay, that's it. Isn't that a nice video? All right. So, okay, that's the basic idea for how we're going to do linear programming queries on convex polytopes fast. All right, so there are a few things that are different about that video versus what you would do for convex polytopes, but they're mostly in presentation. I mean, one of which is that this data structure generally applies to planar graphs. And as we know, doubly connected edge lists or the boundaries of polytopes are all basically planar graphs at the end of the day. And so you have to imagine that you could take that triangulation and then lift it up onto the boundary of some sort of sphere, and then it will exist as like the boundary of some convex polytope. Right, so we should really not think of these triangulations as like living in the plane, but we should actually think of them as living on the boundary of some sphere, right? The other point is that he was considering the problem of locating a point in one of these triangles, right? But that's really the same problem as, say, okay, given some point far away from the sphere, locate the face that happens to be closest to that point. Right? So this could also be thought of equivalently if we took a point that was not on the sphere, project that ray right from the center of the sphere out to that point and locate that closest face, and then that will become the point containing that query point. Right? So it's really not a big step from locating a point inside a triangulation to doing linear programming on some convex polytope in 3D. Right? It's exactly the same problem. So okay. So that's the idea, right? And also it's very useful, I think, to see that video first, because you'll now have something in mind for how this stuff all is supposed to look. And then when I try very desperately to draw this stuff on the on the whiteboard here and then fail, it'll maybe not look so bad, right? But okay. Right, so this is the high-level idea. And this data structure that we're going to see here is called the Dobkin-Kirkpatrick hierarchy. It was pretty much invented to solve this problem of detecting collisions between convex polytopes efficiently in 3D, right? So the idea is start from a fine convex hull and coarsen it by deleting vertices. This is the idea. So here's sort of a picture. So imagine that this is just like a little chunk of a convex hull that I'm drawing here. So maybe I have something looks like this. Put a vertex here, here, I don't know, some here, right? So imagine let's put another vertex right there. Maybe I've gotten a little carried away here. All right. Should also say one thing, which is that these drawings become really horrible looking on the blackboard. So we start off with some triangulation of the boundary. I mean, it's just going to be like some convex polytope right here. Take some vertex like this, maybe select this vertex. And then we just decide that we're going to go blow up those vertices. So we'll just cut them out from the triangulation. And we're going to create a new triangulation, which I'm going to have to draw again.
How do you know how many to delete?
The idea, we'll come to this in a moment, right? Which vertices you delete becomes a very sort of subtle point, right? And that's actually where really the trick is. And how many you delete is actually important, right? It turns out the specific vertices are not as important as the way in which they are selected. This sounds cryptic, but maybe not so much. I don't know. Yeah, that's still connected there. OK. So this is the idea. So I deleted this vertex and this vertex, and then I'm now going to be creating this this coarser version of it. I mean, maybe not a lot coarser in this case, right? And then what I will do is for these new faces that were created, I'm going to store pointers back. So these faces here, I'm going to store pointers to these faces. And then this face here is going to store a pointer to these faces. Same here, right? You can think of it as that it's basically storing a pointer to all of the faces that were incident to that vertex. All right. And then the idea is that when we do searches on this data structure, we're going to start at this fine level, right? So we'll just keep iterating and coarsening it until eventually, right? So if we just keep going, eventually we'll just end up with like a tetrahedra, right? Or like some trivial thing, right? Where if we wanted to do sort of a search on this tetrahedra, we could just check all of the 4 faces and then drill down as necessary. So that's the idea. So the first question here is how big is this thing going to actually be, right? Because if this data structure is too large, then we're going to have problems. But it turns out it's actually not so bad, right? Assuming that we can make the following type of reduction. So here's the idea. So we'll call this layer, T0, call this layer T1, etc. And this will just be, say, like Tm. So imagine that there's m different layers of this triangulation, right? So here is the main argument, or the whole key to this thing, right? So here is the concept, right? Or this is what we would like to achieve, right? It's our desired thing. So we would like that the number of vertices in level Ti, right, is going to be on the order of some constant factor times Ti minus 1. So in other words, it should be like for 0 less than c less than 1, right? So we want to basically find some little parameter c, right? So that as long as we can like kill off some fraction of the vertices, right? And so it better be like an actual fraction, something which it grows linearly as the number of vertices, then this triangulation will ultimately terminate, right? Or it won't get too big. The reason for this is that the total size of this triangulation, if this is true, right? Not a lot of space here. Maybe I drew that too large. But the total size of this, right? So the size of the 0th level will just be n. So that's like the size of T0 because we start with n vertices. Then the next one is going to be c times n, right? Or at least less than or equal to c times n. So we want that this thing is going to be less than or equal to that, plus c squared n, and so on, right? So this is a geometric series, right? And so this is going to be equal to 1 over 1 minus c times n, right? This whole sum. So if this is true, then the total number of nodes in this entire tree of triangulations is order n, right? Because this is a constant here, assuming that the c is a constant, right? So what this implies is the size is order n. And even better yet, if we can select these vertices to delete in linear time, it'll actually take only linear time to construct this whole crazy triangulation data structure. So that's the idea. And if this is also true, the number of levels of this tree is going to be log n, right? So this also implies this parameter here was m, which is like the number of levels. So m is going to be in order log n. And now, does anyone know what the constant on the log is, or like the base here, right? It's actually not going to be too great if c is too large. Any takers? That, or guess, should be about 1 over 1 minus 1 over c, something like that. Or 1 minus 1 over c, yeah. Yeah, 1 over 1, I don't know, not enough space there. But this is the idea, right? So, okay. So here's the question then. So if we're given some triangulation, how do we delete some constant fraction number of the vertices from it? So then we can just retriangulate the holes that are left and then fill it in, right, in order to build the next level. Right, so that's the key constraint. Okay, I'm going to have to erase some stuff, unfortunately. Yeah, now I need to go draw this again. I'll draw it small. Right, so some boundary of a convex polytope. It's just going to be like a bunch of triangles. So here's the idea. We want to delete as many verts as possible such that no two are adjacent. Well, why? Right? Well, if we delete two adjacent vertices in one of these levels, then we're going to be left with some hole that's not going to be convex, and it will actually be really hard to retriangulate that hole. So we basically want to select some collection of vertices, right, so that no two are adjacent. Another word for this in graph theory is it's called an independent set. So we want to find an independent set in this graph. Another way to say that is, I'll just say given a graph G equal VE, an independent, or we'll actually say some set I contained in V, right? So some subset of the vertices is independent, right? If for all distinct pairs of vertices in I, right? So if we take any pair of vertices x not equal to y, the edge xy better not be in E. Right, so if we, another way of saying this is that any pair of vertices here would be not intersecting. So for example, in this graph, if I take this vertex and this vertex, maybe, no, not that one, right? Maybe this vertex. And this one, right? So these vertices are all independent because they don't have any common edge between any of them, right? On the other hand, if I take like this vertex here, well, then this would no longer be an independent set because it's touching this vertex. They have a common edge, right? So this is the idea. Now, it turns out that finding a maximum independent set, which is finding the largest possible independent set for a graph, is actually extremely difficult, even for planar graphs, right? So it's actually an NP-hard problem to construct a maximum independent set. However, for planar graphs, it's relatively easy to construct a pretty good approximation by just doing the obvious greedy thing, which is take an arbitrary vertex, right, and then just take the next vertex which is available and just keep doing that until eventually you've built an independent set. Formally, here's the simple algorithm for constructing a maximal greedy set, right, or a maximal independent set. Right, so not a maximum independent set, but maximal. Right. Should probably write that down. So maximum versus maximal. This is one of these annoying pieces of, someone thought they were being very cute. So maximum with the UM at the end equals largest possible. independent set, a maximal with the AL at the end instead of a UM is cannot add any more verts to I, right? So in other words, if you added even one vertex to the independent set, it wouldn't be independent anymore. So in this graph here, the vertices that I've selected, I believe that this is a maximal independent set. I don't know if it's maximum, probably not. But yeah, I mean, if you look here, if I take any of these remaining vertices, can't stick them in there, right? It's just not going to work anymore. All right, so here's the idea. So maximal independent set, we'll call it maximal IS, and we'll just say we give it a set V and E. The idea is very simple. We initialize V to the empty set, march over the vertices, say for Vi in V. We say if Vi incident to I, skip it. Otherwise, just stick it in the independent set. Right? So we'll basically set Vi. All done, return I. Trivial, right? No big deal, right? In fact, we can actually keep track of the vertices which are incident to I by just marking them in a table, right? So when we add a vertex, we just march over all the edges incident to that vertex. And so the complexity of doing this is order n. So here's the simple thing. We can find a maximal. I'm going to write independent set in ON. Okay? And now here is the punchline from all of this, which I won't even bother to prove, but it's actually very difficult to make this proof, and this is actually where most of the work goes in proving this, unfortunately. But we don't have unlimited time here. So this is kind of a proposition. If you take a course in like advanced algorithms, like this is probably one of the things you might see in that, right? So this type of result. But it turns out for planar graphs, this ends up being about order n, right? It actually ends up being about 1/6 times the number of vertices. So for planar graphs,
talking about the number of points in it.
For planar graphs, the output from this thing will end up being about 1/6, 1/12, somewhere in this ballpark. So this ends up being about 1/6, then, which is order n, all right? It's just for planar graphs, if you just do the simple thing here, right, you will get an independent set that's about n nodes, with maybe not a great constant in front, all right? So given this, we can construct a hierarchy of triangulations, right? Now, with that hierarchy of triangulations, we can do fast point in convex polygon tests, right? So how does that work? Well, okay, let me kind of erase this a little bit. Is this okay to do that? Right. So I'm going to draw sort of a schematic view of this, right? So here's kind of our idea. Imagine this is convex, right? There's some polygon, it's very fine. Maybe inside we have like a coarser version. This continues until ultimately we're stuck with like some simplex down at the very coarsest level. So we can imagine that this is our hierarchy, and we have edges that point out, from each level to the next level. So each of these guys has pointers. And the number of these pointers is bounded by the degree of the vertex that we deleted, right? So how do we do point location? So we'll say that we have some triangulation T, and we have a query point Q, right? Or we have this hierarchy. We'll start from the coarsest level. So first, test Q against all faces of T if face is terminal, which is that it's not like linking to any other finer faces, return face. Otherwise, return point location of the farthest face with Q, right? That's maybe not the best description of how this works, right? But in sort of a high-level, very sketchy way, it's basically what's going on. So here's how we would imagine doing this. So suppose I take a point here, right? Call this Q. What we do is we just loop over all of the faces at the coarsest level. Say this one happens to be the one which is closest to Q. So then we'll just expand out on that level. So then we now go search the faces here. Maybe there's like more faces, something like this. So we then expand out here. And then we just keep going until eventually we reach some fine level, and then we're done. So the cost of this is basically proportional to the number of these additional faces that we have to search out, right, when we do the subtriangulation. So sort of and the number of these additional faces that we search is going to be proportional to the degree of the vertex that was deleted. So this is going to be, overall, the running time, right, will be order number of levels, right, which is log of n, plus our times, not plus, times the maximum degree of any vertex v, which is going to be constant, or we can expect that this is maybe about 6, right, in a planar graph. And so this will end up being about order log n, this very sketchy thing that I just kind of showed you how this works, right? So, okay. How can we use this to do collision detection or intersection tests? Yeah?
What do we define as a farthest face then?
You can imagine that when you take one of these faces, you get these pointers, right? So these should actually, well, let's just call this children of the farthest face, right? It's maybe a better way to write this. And this is probably not the best thing. If you want to look up how this works in more detail, you can look at DeBerg, the textbook for this course. In the chapter on Delaunay triangulations, they cover this. So there is a little write-up there, probably on page 195, where they talk about it. And I can also send some papers if people are interested in it. So yeah, okay, the idea is that but when we find this farthest face, right, what we're going to do is we're going to expand out one layer down the tree by going into all of the children of that face, right? So if you remember how it worked in the video, right, you get to a face, then this is going to be linked to a bunch of subfaces. You do the search in each of those subfaces, then you continue, right? And so each time we go down to like another level, we just search through all of the faces that we have to in that level, then we go down another level, and we just keep going until finally we reach a terminal face, and then we're done. So, one kind of picture of what this, another way to kind of visualize what's happening here is that we start with the polygon, we triangulate it, then we refine each of these triangulations, then these triangulations are themselves refined, and so on. And this is pretty much, for the case of 2D polygons, right, we don't even really need a data structure. We can just build this directly from the list. And that's essentially what was going on with the intersection algorithm in 2D, right? It's just in 3D, because we have to be a little more careful about how we cut off these faces and refine it, we need to build this triangulation hierarchy first, right? So if we have two of these, refined triangulations, right? Then if we want to find, like, say, a closest pair of points, what we do is we start at, like, this coarse level. And again, we'll run into the situation where we have to compare the two features, right? So we find either, like, the closest vertex and triangle or closest vertex edge, just test all of those different configurations, and then expand, going one level down for each of the faces that were incident to that configuration. And then we just do that until eventually we've reached the finest level, and now we have the closest pair of points, And the number of levels is basically, or the number of steps that we have to take here is we have to take log of n here, where this would be the first polygon, plus log of however many vertices were in the second polytope. All right, so the total complexity of doing this is logarithmic in the number of vertices that are involved. All right, so that's the idea. And you can use this again to evaluate point tests, right? Because it's just tested if it's inside this point, or if it's inside the coarses level. If it's contained inside the coarses polygon, you're done, right? Otherwise, you look at the feature which is farthest from it, and then you continue, going down that level and so on until you either are contained in some feature or you're at a boundary, right? So that's the idea there. Now, there's a couple of other stuff that I wanted to talk about really quickly. Right. So, okay. This is maybe a little sketchy here, but you got the idea, I hope, right? I mean, any real questions about that? Or I think, okay. So I want to talk about one other thing that we can do with 3D convex hulls, which is an application to GIS systems, like mapping and like sort of spherical geometry. So for example, suppose you want to be able to say, given a bunch of points on the surface of the Earth, find the closest point to some given query point. Right? So this could be sort of like, imagine like you need to figure out like where is the closest hospital on the Earth, to a given like query point. So like you're in an emergency, and suppose you don't have to worry about roads or anything like that. You can just like fly there over a helicopter or something, right? Or maybe another sort of related question could be you have a disk and you want to find all of the cities which happen to be contained inside some disk, right? Or maybe you have some sort of zoning ordinance that says that you can't put a daycare center within, like, say, 20 miles of like some paint factory, right? And so you would have to say, like, okay, well, where can I put this paint factory? So maybe you could go put the disk there and then check that there are any like objects that are contained inside that. So these are basically two related types of queries. So that we can answer using convex hulls in 3D, right? So this is, and we can answer them efficiently using convex hulls in 3D plus the Dobkin-Kirkpatrick hierarchy. So this is the idea here. So we're going to call these map queries. Or we'll say, or maybe let's call it globe queries, right? Because we're working on the surface of a sphere. So we'll just say using 3D convex hull plus the Dobkin-Kirkpatrick hierarchy, right? So the first one is find closest point to some query point. Another type of query is find all points in disk. And then we can also do stuff like, say, find closest pair of points on a sphere, right? So these are all on a sphere. All on sphere. So here's kind of a picture. So we're going to imagine like maybe this is the Earth. So I'll have a bunch of these different points out here. Take a query point, like this thing. Then you want to maybe find like the closest point to that query point out of your data set, right? So you're given some data set of, say, n points, all distributed over the sphere. You want to pre-process them in some way that you can support all of these queries efficiently. So any guess as to what you do first? Idea. So we start out with n points on the sphere. What are we going to do with it? First step. I mean, we only really know how to do one thing with the points. Exactly. That's what we're going to do. So the first order of business is take a convex hull of these points on the sphere, right? So first step, so they're pre-processing for each of these queries. Step one, take convex hull of points on sphere. Step 2, compute the Dobkin-Kirkpatrick hierarchy, right? This will turn out to be the expensive pre-processing step. This will take order and log n. This takes order n, so it's pretty much free if we've already done a convex hull, right? In an asymptotic sense, right? So the total pre-processing time for answering these queries is going to be order n log n, and the data structure that we're all left with here, well, this is an order n thing. This is also order n, so data structure is going to be order n. OK, so how do we do the first point, right? Well, let me actually point out one thing here, right? Which is, suppose we compute this convex hull, right? I'm going to draw something here. So imagine I have these 3 points. They're a face of the convex hull. This triangle here, right, will determine some plane. So I can draw this plane that cuts through this sphere that all the points are distributed on. And the intersection of this plane and the sphere will form a great circle that passes through each of the vertices of this triangle. And moreover, in this great circle, there are no other vertices from this triangulation that are going to be contained inside it. So if I have any other data points out here, they can't be contained in this great circle. And similarly, if I lift each of these arcs onto the surface of the great circle, or onto the surface of the sphere, then they're also going to form great circular arcs, which are contained inside this other sphere. Now, this property that there are no other points contained in the circle is actually sufficient to tell us that if 2 points are the closest pair of points in this triangulation over the surface of the sphere, right, then they happen to have some common edge in the convex hull. So actually, this query right here is really trivial, right? Just loop over edges. So and just find the closest pair of points in the geodesic sense on the sphere, right, by just traversing all edges of the convex hull. And when you're all done, the closest pair of points are going to have some common edge. That's it, right? So you can do this in basically n log n time to compute the convex hull, and then order n time to do the scan. You don't even need the Dobkin-Kirkpatrick hierarchy for that. So this is actually a somewhat trivial query, right?
Can you use faster than that?
Yes. We'll get to this later. We'll talk about other data structures and other ways to approach that problem. KD tree will actually take the same amount of time, and it actually will turn out to be much worse than the results that we're going to do today. This is better than what you can do with the KD tree, right? And in fact, actually, if you're working with points on a sphere, you probably want to do this. You don't want to do KD trees. This is a better way to deal with data in spheres, right? But only for spheres, right? There are other reasons you might want to use a KD tree. So, OK, this point here, right? How do we find the closest point to some query point? Well, here's the idea. You just take your query point that you want to test on the sphere. You do a search on the Dobkin-Kirkpatrick hierarchy to find the closest face. You're going to get a triangle, right? So you basically use that search to find the closest face. Then you just check each vertex of that triangle, and then you're done, right? The cost of doing that is really just log n, right? There's nothing else to it, plus the cost of doing that search, which is constant. So this is easy. So this is easy. Order log n, simple search. The last one, though, here, find all points in the disk. The way that we're going to approach this is by, again, thinking of each of these disks that we want to search here as being the intersection of some plane with the sphere. So if you imagine that you have, like, say, some set of points out here. Let's draw them. I'm kind of low on time here, right? So imagine we want to search all points which happen to be contained inside this disk. You can think of this as basically being like a half space, right? Where we have this line that cuts them out. So here's what we'll do, right? We're going to first do a linear programming query, again using Dobkin-Kirkpatrick, to find the farthest point along the axis of the plane. So this is the idea. So we first find some point out here, right? So now we've got a point which is as far away as you can possibly go along the normal direction of the plane. And that point, we can either say, if it's inside this half space, right, then we have at least one point there. But if it's outside, then there's actually no points inside there. So this disk doesn't contain any points at all. So we can very quickly check whether or not this thing is contained in a half space or not contained in a half space. So if it does happen to intersect the half space in some way, and we now have this farthest point, then we can locate the rest of the points which happen to be contained in this half space by just marching, right? Because we already have the topological information we need in the convex hull. And this marching operation is going to be proportional to 1 for each additional point that we have to query, which is the bare minimum, plus the original overhead of doing that search. So we can do this in order log n for the initial extremal point query, right, that we have to do with the half space search, plus k for the number of points that we have to actually report within that half space. So I think at this point I am almost completely out of time. So I'll just take any questions for this or any comments on it. So does this make sense, right, this idea? I didn't write out the code for it, but we're pretty much done with class, unfortunately. I mean, does the idea make sense? We'll come back to these, and we'll see this in another perspective, right? But I will also say, I can say one more thing here, too. I can actually show you a picture of what all this looks like. So here, right, this is the last thing I wanted to do. No. OK, right, one last thing. OK, I'll show you a picture of this, and then we can go. So this type of data structure, which is actually just a convex hull of points on a sphere, is sometimes called a spherical Delaunay triangulation. But it's actually just a convex hull, right? We'll see how to do this for points in the plane next time. And we'll go into much more detail about how you can calculate these sorts of operations or these types of queries for planar points. OK. But here's basically what this looks like. Oh, right. I should also point out the dual of this convex hull is going to be a polytope where each of these faces consists of the set of all points which are closest to any given vertex on the sphere. So the lines that you see on this sphere are actually the faces of the convex hull projected onto this space. And then these blue lines here are these great circles that you get when you intersect the plane, which is tangent to that face, with the surface of the sphere. But this is literally just the convex hull of these points. And you can actually insert other stuff into it. So that's just a picture to kind of play around with it. We'll explain more about this for planar collections of points, not stuff that happens to live on a sphere, next time, right? Right. Now I'm going to stop.